All right, today I'm joined by my TA Serenity for this statics video on dot product. In statics, you'll find two uses for the dot product. One is to find the angle between two vectors, and the other is to find the component of a diagonal vector that is parallel or perpendicular to another vector. And that usually occurs when you have a force vector that is partially stretching a component and partially bending it. So we're gonna do one problem of each type. Let's go. All right, so first problem using this figure shown, solve for theta. What is the angle between these two vectors? And before we even get into the dot product equation, the most useful thing you're gonna need to find is the x, y, z coordinates of each point in this problem, A, B, and C. So I highlighted the x, y, and z coordinate directions. And from that, you can see that point A is at +2 in the x direction, -3 in the y direction, and then +3 in the z direction. So I've labeled the XYZ coordinate for point A, and point B is at 0 in the X direction, +3 in the Y direction, 0 in the Z direction. And then lastly, point C is at -2 in the X direction, the same +3 in the Y direction, and then +4 in Z. There are two ways to calculate the dot product of two vectors. If you know the angle, then you can just multiply the magnitude of both vectors times cosine of the angle. Or if you know both vectors in Cartesian form, you can use the first version where you multiply the x components, add that to multiplying the y components, and add that to the multiplication of the z components. We can also use these two different versions of the dot product to solve for one of the components, in this case the angle. So the reason I figured out the x, y, and z coordinates at the very beginning for points A, B, and C was because I was going to need these position vectors from A to B and from A to C. And I solved for each of those position vectors by subtracting the final position minus the initial position. So B minus A and C minus A. So from the generic dot product equation, I'm using RAB as one of my vectors and RAC as the other one of my vectors. And so I labeled that I'm going to be plugging this -2 in for AX, the 6 in for AY, the -3 in for AZ, etc. To get the magnitude for both of these position vectors, essentially do a three-dimensional Pythagorean theorem where I square each of the Cartesian components. And now you can just plug everything in. And so the angle between vectors AB and AC is 36.43 degrees. And we got this by first calculating the position vectors from A to B and A to C using their individual XYZ coordinates of each point, calculating the magnitude of each of those position vectors, and then setting both versions of the dot product equation, one that has cosine theta and one that has the Cartesian components, and setting those two versions equal to each other and solving for the unknown angle. Now, this second problem type is not going to be used very much here in statics, but this is something that you'll use in a follow-on course, Mechanics of Materials. In Mechanics of Materials, we'll look at problems like this pictured here with a metal pipe, and with this diagonal force applied to it, what we want to know is how much of this force is causing the pipe to either stretch or compress, and then also how much of this force is causing the pipe to try to bend. And we're going to do this by figuring out what component of this 3 kilonewton force is acting in the direction of the pipe, and then oppositely, what component is acting perpendicular to the pipe. The portion of the force acting in the direction of the pipe is going to be causing tension or compression, and then the portion acting perpendicular to the pipe is going to be causing bending. And even though the angle is labeled on this drawing, we're going to be able to figure out these projections without actually using the angle. Instead, we're going to be able to use just the position vector, and in particular, the unit vector for the pipe. So again, we are going to need XYZ coordinates for all of the relevant points for this problem, which are going to be B, C, and D. Well, point B is at the origin, so that one was pretty easy. So point C is at +3 in the X direction, +4 in the Y direction, and then -1 in the Z direction. So point D is at 8 in the X direction, and keeping note that there is a number 5 right here, but this 5 only measures to that point right there, so you also have to account for this 3. Then it's at 0 in the Y direction, 0 in the Z direction. So the next step for this problem is going to be to use these XYZ coordinates for each point in order to find the unit vector pointing from B to C, which is the direction of the pipe, and then from C to D, which is the direction of the force. And remember, a unit vector is a position vector divided by the magnitude or the length of that distance. So a unit vector points in the correct direction, but only has a length of 1. So since B is the origin, the position vector from B to C is actually just the location of C. You then find the position vector from C to D by taking D's position, the end of the vector, minus C's position, the beginning of the vector. The magnitude of each of these position vectors, which is the length or the distance as to how far apart each of these points are, can be found by doing a big square root where you square each of the XYZ components, right? This is just like a three-dimensional Pythagorean theorem. And to put some numbers, the unit vector, again, is the position vector in Cartesian form divided by the magnitude of that Cartesian vector. And your answer for a unit vector should all be decimals, values between 0 and 1, because the magnitude of the unit vector will equal 1. So none of its terms could be larger than 1. So we get the force vector F by multiplying the magnitude of the force, which was given on the figure 3 kilonewtons, times the unit vector that points in the direction of the force. So F equals Fu. No laughing. All right, I promise we're almost done. This is the last step. When calculating the dot product, I did find that I had a sign error in this last step, so I highlighted it here to make sure if you're following along in your notes that you don't make the same mistake. So in order to calculate FBC, that is the component of the force vector in the direction of pipe BC, you do a dot product between the force and the unit vector that points from B to C. And you do this by just multiplying the X components, the Y components, and the Z components, and adding them all together, and you get a single numerical answer. And this numerical answer is the amount of force in tension or compression. Since we get a negative answer, this means that the force is actually in compression, that it's slightly squeezing together pipe BC. And to check whether this answer makes sense, notice that it's very small. We started with F of 3 kilonewtons, and the answer is 0.18 kilonewtons. But look at the direction that F is pointing. F is pointing straight off to the left, while the pipe is going kind of mainly upwards. So it looks like the force is mainly going in the other direction. Very little of F is actually pointing in the direction of the pipe, so it makes sense that this answer should be very close to 0. And if you also wanted to find the perpendicular component, that is the amount of force that is perpendicular to the pipe, which is causing bending in the pipe, you can get this using a simple Pythagorean theorem, because the parallel version and the perpendicular version are essentially the two sides of a right triangle, and your force is the diagonal. We started knowing that the force was 3 kilonewtons. We already saw for the parallel component in the direction of BC. It's a little bit of math. We see that the perpendicular component is 2.99 kilonewtons, which, as I already said, kind of makes sense from the picture because it looks like the force is almost entirely in the perpendicular direction. So it makes sense that that answer should be very close to 3. There's a lot of YouTube videos out there about dot product. Thank you very much for watching mine. I really do appreciate it. And if you want to move forward in statics, the next video to watch is going to be this one about free body diagrams and particle equilibrium, writing your equations of equilibrium. Thanks for watching and enjoy the rest of your day.